Right, so thank you very much for the invitation to speak. I'm going to be discussing some work done with Shutong Zhao, Meng Cheng, Tyler Ellison, and Tibor Rakovsky, who's sitting over there. Right. So I'm going to start with the punchline of this talk, which, because there are various technical details, I'll just say what it is that we're trying to say. So judging from the faces in the audience, I think most of you probably know what topological order is. When we think about topological order, you should have in mind things like the toric code or the fractional quantum Hall effect. And something that is true, at least of these well-known topological orders, is that they are not stable on coupling to a finite temperature bath. Right? So in the fractional quantum Hall effect, it's naturally actually coupled to a finite temperature bath. But what you find is that as you make the devices larger and larger than a thermal coherence length, all of the beautiful properties of the fractional quantum Hall effect disappear. So in fact, it's something that only exists at finite size. But things like the 2D toric code are likewise unstable at finite temperature. And there's there is a kind of general belief that many of these models that we know and love are unstable on coupling to a thermal bath. So at least in low numbers of dimensions, as in dimensions less than 4. So what I'll tell you about today is a model in 3 spatial dimensions, which in a certain sense has topological order at low but non-zero temperature. And in fact, it's a model that is already to some degree known as a zero temperature phase. It's something called the 3-dimensional fermionic toric code. And so what I'm going to try and argue today is that this model is at finite temperature topological. I need to give you a definition of topological. I'll do that in a few slides' time. Okay. Right. So, and also just to give you a bit of a sneak peek as to what it is that makes this state special. The way that we show that this state is non-trivial or topologically ordered has to do with some symmetries of the states. Probably a lot of you have encountered this language before, which is to say that the state possesses a higher form symmetry. Okay, so this state, what it'll all amount to is that this state has a certain symmetry which is incompatible with the thermal density matrix of this state being trivial or non-topological. Okay. And, well, don't be afraid by the words higher form symmetry. What I really mean is that there's a line-like operator such that when you take the thermal density matrix and you multiply it by this line-like operator, it's fixed. But that this line-like operator has an interesting, what we call anomaly, which is to say that if you open up this line-like operator, it basically creates excitations that look like fermions. So in a certain sense, this fermionic toric code has, even though its underlying degrees of freedom are bosonic, it has these emergent fermions. And having these emergent fermions is incompatible with the thermal density matrix being topologically trivial. Okay. That's roughly what's going to happen. Okay. All right, so that's the motivation. And, that's the punchline and the motivation all in one slide. So now what we're going to do is, I've used the word phase and topological phase, so I'm going to just say a few words about how we go about defining things like phases and topological phases. So perhaps the old-fashioned definition of a phase is you have an experimentalist and they have some knobs that they can twiddle, and a magical thing happens where you have contiguous regions, and the sort of knobs are sort of labeled on the axes here, and you have these contiguous regions where the long-distance correlation behavior looks the same, and that's what we call phase. Well, that's the sort of first definition of phase that we come across in condensed matter. But more recently, particularly when it has come to classifying things like the ground states of gapped Hamiltonians, we have a more, sort of, in some ways, operationally more useful definition of phases, which is in terms of the ground states of many-body Hamiltonians. Basically, we say that 2 ground states are in the same phase, psi and psi prime are in the same phase, if there's a simple operation or low-depth unitary circuit, we say, that connects the 2. So roughly speaking, 2 wave functions are in the same phase if there's a short time evolution or essentially a local change of basis that relates the 2 wave functions together. And one of the things that a number of people, but particularly Xiaogan Wen and Matthew Hastings showed is that this definition of phase is more or less the same as the above notion of phase for the ground states of gapped Hamiltonians. And so this is a kind of useful perspective, and it's when I come to defining the topological order in 3D phases, it'll be useful to have this sort of picture in mind. Any questions about that sort of background? Because now I'm going to talk about what it means to have a density matrix that has topological order. That's in an interesting phase. Okay, no. All right, good. So probably this will annoy some people in the audience, but the way that I'm going to define topological phase is I'm going to do it in a kind of roundabout way. I'm going to say what a trivial phase is, and then I'm going to say a topological phase isn't that. All right? Okay, now this is not, the definition of topological phase that I'm giving you is more or less the same as some that already exist in the literature. I'm thinking in particular of Matthew Hastings' paper from almost 15 years ago on defining topological order at finite temperature. So let me give you this definition now. So right, we want to understand when a density matrix is special. So let me define a trivial density matrix, a density matrix that isn't special. Okay, so there are a few steps here, but here is a trivial density matrix. So I need to sort of unpack what's happening in this expression. I'll say that a density matrix is trivial if it's basically an incoherent superposition of short-range entangled states. Okay, so what I mean by that is it's some sort of diagonal sum of states that you can easily obtain from a product state with a low-depth operation. So think of the sorts of things that experimentalists can do in real quantum simulation experiments. They can prepare product states and they can do simple local operations on those. Each of these SRE states is of that form. Okay? There's an extra layer of complexity, which is that I'm also going to allow my experimentalists to do an extra layer of operations on top of that with a local quantum channel. So this is a kind of operational definition of a trivial density matrix. It's something that you can get by starting with a product state and doing some simple operations on it, simple low-depth operations on it. Okay? Maybe, yes? Also ask that rho trivial. No, I do not ask that rho trivial has cluster decomposition. So for example, e to the minus beta j zz, where beta is, where T is below the critical temperature, that's a classical Ising ordered phase, that will be trivial by this definition. So in other words, it's this notion of triviality is put in here to sort of distinguish all the kinds of thermodynamic classical phases that we know and love from something that's topological. Okay, all right, good. So very good question. Yes. Yes, that's right. So it's a picture that looks something like this. So, you know, your state comes in here, and each of these things is basically a two-site gate. And you're only allowed to, let's say, a few, I'm being, like, you're not allowed this, for this circuit to be too deep. It's not allowed to, for example, scale linearly in system size. Okay? And when we say low depth, we actually only allow it to scale logarithmically in system size. And that's enough for triviality. All right. Yes. Right, so, okay, so what it is that we're going to try and prove is that this fermionic toric code thermal density matrix is not of this form, okay, provided you're below the critical temperature. And to show that, what we're going to do is we're going to look at the distance between the fermionic toric code density matrix and trivial states of this form, and we're going to show that the distance is large. Or in this case, you know, either the fidelity is decaying faster than any power law in system size, or the trace norm distance is almost as large as it can be. Okay, right. So that's what we'll show. Yes. I don't think that that's important, but I think it probably is equivalent because you could probably store this I in some local ancilla that you use it could sort of locally encode what each of these states is doing, and then you could just have a. I'm actually not totally sure. I'm not totally sure. I might have to think about that a bit. Yeah. All right. So before we talk about this funky three-dimensional topological order, let's just talk a little bit about the topological orders that we should all know about. So I'll talk about the 2D toric code. I'll give an intuition as to why it's unstable at any finite temperature. I'll talk about the 3D toric code, and I'll explain to what extent it's unstable at finite temperature. And then I'll present a small modification of the 3D toric code, which is this 3D fermionic toric code. and I'll try and explain why it's non-trivial. Okay, all right. Okay, this slide looks a bit different because this is one of the very first slides I ever produced for a talk when I was a graduate student, and it turned out to be useful again here. And I spent ages putting this on Beamer, so I decided I'd get value for my time investment. So here is the 2D toric code. It's defined on the honeycomb lattice. I will choose to define it on the honeycomb lattice today. Whenever a bond has a spin down, there's a spin half degree of freedom on each bond. Whenever it's pointing down, I'll color the bond in, otherwise I'll leave it alone. So here's a spin configuration. And probably we all know that the toric code is a commuting stabilizer Hamiltonian. There are vertex terms and there are plaquette terms. And they all commute with one another, and they can all be minimized simultaneously. Okay? And when we do that, we get the toric code ground state. So there are these vertex terms. Vertex terms, like it, would prefer for lines of flip spins to never end, right? They just want the ground state to look like it has closed loops in it. Okay. Plaquette terms hop the loops around. So satisfying the vertex constraint says my ground state is only going to contain closed loops. Satisfying the plaquette constraint means that my ground state is going to essentially consist of an equal sum coherent superposition of all of the loop states. Okay. All right. So that's essentially what this slide is saying. So I'll just sort of skip over that. You solve all of these constraints on the torus, and you get 4 ground states. Okay. So each of these is a sort of loop gas configuration. It's all a sum of closed loops. There are no open loops with endpoints. But it turns out that because you can't deform any of these pictures to any of these pictures, because they have different global winding parities, that you end up getting a Z2 ambiguity as to what the boundary conditions are on each cycle of the torus, and you end up getting four degenerate ground states. Okay? And indeed, it's these 4 degenerate ground states that we tend to use to store logical information in the toric code. And it is to some extent stable, at least when you're at 0 temperature. Okay, so that's the toric code. It's topologically ordered. One of the ways we can see that is has these topological degeneracies on different manifolds. But perhaps a better way of seeing this is to consider the excitations of the model, and this will be a useful perspective when we come to consider the 3D fermionic toric code. So I told you what the ground states were. I didn't tell you what the excitations were. There are 2 types of excitations. We'll call them E and M particles. You can think of those as particles and fluxes. The particle excitations you get by selecting a path on the lattice and flipping all the spins along the path. It turns out that this operator commutes with the Hamiltonian except precisely at its endpoints. And so it creates an excitation that has scale 2 times whatever the gap is, because it creates 2 of these excitations at its endpoints. And it also has M-type excitations, which are formed by acting on a bunch, looking at a path on the dual lattice and acting on each of the bonds, crossing that path with the sigma z, and this creates 2 plaquette excitations. And the important thing about this, an important thing about these excitations is that they have a relative statistic with one another. In other words, if you take one of these particles and you braid it around a flux, you get a relative anionic statistic, a relative semionic statistic. And this is actually a sort of equivalent. Or more or less equivalent to it's equivalent to the fact that this model has ground state degeneracy on non-simply connected manifolds. So I'm just going to sort of pause here and just to sort of hammer this point home. The toric code possesses an interesting higher form symmetry, okay? Which is to say, in this case, what that means is it has a kind of loop symmetry. You take the toric code ground state and you act with a bunch of sigma x's along a closed path. So that's this vertex creation operator, but you sort of close up the endpoints. The ground state is exactly fixed under that operation. So it's like a symmetry, right? It's also, by the way, a symmetry of the Hamiltonian in this case. Likewise, if you act with one of these M excitations in one of these M operators in a loop, you fix the ground state. So this ground state is fixed by a number of these loop-like operators, and I'll say that it has a higher form symmetry. But there's also something special about this higher form symmetry, which is that if you sort of open up one of these E excitations and then take an M excitation around that, so you take your state, you insert a pair of these E particles, and then you take an M around a loop, you get a relative minus sign, and this is the relative semionic statistic that I was talking about on the previous page. And so the point I want to make on this slide is that it turns out you can show that any state psi that has this property, it has this one-form symmetry, and the operators that implement that one-form symmetry have this kind of statistic. You can show that any state that has those properties is necessarily not trivial. In other words, it's necessarily not related to a trivial product state by low-depth operations. In other words, this sort of symmetry means the state is interesting. And there's this is, to some degree, been known for a while, but there's a very nice, clean, crisp analytical argument which actually bounds the fidelity between any state that has this property and trivial states. Basically tells you the fidelity has to be decaying faster than any power law in system size if a state has this property. And that's the sort of argument we'll use later. Okay, so now what about at finite temperature? So finite temperature kills the 2D toric code, and the simplest way of seeing this is a kind of piles type argument. We know what the excitations of the model are. They're these point-like excitations. If you create a pair of point-like excitations, you pay an order 1 energy cost, no matter how far separated they are, because you just violate 2 terms in the Hamiltonian. So you pay 2 times gap. Okay? Okay, so that's the energy cost. The energy cost is like delta. If we're doing a free energy calculation, let's say the sort of if you're doing a free energy cost, maybe you want to look at beta times delta instead. So we have this beta delta, that's encoding the energy cost. But what's the entropy associated with having a pair of point particles in a system? I can put them anywhere in the system. So that's L squared places. And so the entropy gain from this is going to be log L squared, which is basically log L. And log L is bigger than beta delta when the temperature is finite. So in other words, it always makes a free energy sense to propagate or to proliferate point-like defects in this model at finite temperature. Okay? So as soon as you couple the system to a bath, as soon as you do that, these point-like particles proliferate everywhere. And your state loses this nice one-form symmetry, because now the particles are everywhere. So if you try and move, let's say, a particle in a big loop, which is that big circular E operation from the previous slide, try and move one of these particles in a loop, there are a fluctuating number of fluxes in that loop, and so you don't get back the state exactly. You get back the state is not fixed by this operation anymore, so you lose these one-form symmetries. And also there are just more direct proofs that at any finite temperature, there's an explicit way of decomposing the thermal density matrix into a sum of short-range entangled states. Okay? So basically, we know for sure that none of this order is preserved at finite temperature. And also, like, the sort of intuitive picture is that at finite temperature, all of these things percolate across the system, and so you also lose any logical information you had stored in the toric code. All right, so that's the 2D toric code. So you might wonder what happens in the 3D toric code. Which is, yes? No, it's in the thermodynamic limit, the quantum Hall effect is not stable at finite temperature. What actually happens, maybe it's most instructive to ask what happens in the devices. So there's a length scale associated with the temperature, which is basically the phase coherence length, or which is basically a coherence length. And once the devices get larger than that, the plateau is washed out. Maybe the picture you should have is that there are anions proliferating everywhere in the bulk, because it makes free energy sense. You create 2 anions, you get 2 times gap energy, but there's a heck of a lot of entropy once the system is large enough. Yeah, but the devices are in a regime where actually log L is competitive with beta delta when you do see the plateau. Okay, so 3D toric code. It's on a 3D lattice, on the cubic lattice this time. There's a spin degree of freedom on each bond of the lattice. I'll again color it in if it's pointing down, leave it alone if it's pointing up. There are 2 types of terms in the Hamiltonian. It's again a commuting stabilizer Hamiltonian. There's a vertex term, which is going to make the ground state want to look like a superposition of closed loops. And there's a plaquette term, which will tend to hop the loops around. And when you satisfy both of these things, the ground state looks like a loop gas. Okay? If I put this model on the 3 torus, I get a ground state degeneracy of 8. This corresponds to the fact that around any given direction, and there are 3 directions, you could have any of the Z2 parity winding numbers. Here are some not particularly good quality pictures of loops in the different topological sectors. So again, this model looks topologically ordered because it has this ground state degeneracy, and again, it has two different sorts of excitations. Again, has point-like excitations, which I'll call charges. The one difference now is that instead of having point-like fluxes, it has vortex rings. It turns out that there's a relationship between plaquette defects going around a cube, which basically says that the number of plaquette defects around a particular cube is always even, which means that these lines of plaquette defects have to form closed loops. Okay? So there are two sorts of excitations. You can create a pair of vertex excitations by flipping the spins along a line. You can create one of these vortex rings by taking some surface and acting with sigma z on every bond that cuts the surface, and that will create a vortex excitation at the perimeter of this surface. Okay, and once again, yes, oh yeah, and another thing to highlight, and I'm going to highlight this for sort of a reason that will become clear a bit later, is that these point-like excitations basically behave like bosons. So, in other words, if you do a braiding experiment or an exchange experiment with two of these particles, you get a bosonic self-statistic. So, for example, swapping particle 2 and particle 3 here will give the same configuration with no phase. We'll give the same particle configuration with no relative phase. If these were fermions, there would be a relative minus sign between these two figures. Okay. All right, I'm highlighting that because in the fermionic toric code, the point-like excitations are going to be fermions, and that's going to be very important for our argument. Okay. All right, so what happens to the 3D toric code at finite temperature? Well, once again, at any finite temperature, the point-like defects will proliferate. It's the same entropy argument, log beta beta delta. So at any finite temperature, we have some C of these point-like vertex defects. The story with the vortex excitations is more interesting, because if you think about one of these vortex lines, the energy associated with the vortex line of length L is proportional to L. It's a beta times the energy is beta L. But the entropy associated with it is also of order L. Turns out that the number of loops of length size L scales exponentially in L, which means there's an entropic gain of L. So there's actually something to be balanced there. It's like the traditional Piles argument for ordering in the 2D Ising model. And so, in fact, there's an ordering transition at a finite temperature where the entropy ends up beating the energy cost of these lines. So at zero temperature, everything's lovely and topologically ordered. At any finite temperature, anywhere along this line, the vertex defects proliferate. In this region, the loops are short because of the Piles argument I just gave you. And in this very high temperature region, everything proliferates, the vortex lines and the point particles. And so one question you might ask is there anything non-trivial about this phase over here? But in fact, you can prove, Hastings proved that you can disentangle the state here. It has been proved that the thermal density matrix at any non-zero temperature is in fact trivial in the sense that I said on the second slide. So you might think that this means we're sort of our ambitions of writing down a 3D topologically ordered state at finite temperature are doomed. And it probably has something to do with the fact that point-like defects are proliferating. But we're going to say not so. Any questions about this so far? Okay, all right. So, fermionic toric code. A very slight modification to the toric code. Has the same vertex term as before, so already we know that the ground state is going to have closed loops. It has a slightly different sort of plaquette operator. So previously, the plaquette operator, you'd go to a plaquette and you'd flip the spins on each of these red edges, on each of the edges on the boundary of that plaquette. The one subtle difference now with the fermionic toric code is that there's a configuration-dependent phase associated with that flip. So what that means in practice is that the plaquette terms end up having these flips, and then they also have some Zs at some strategically chosen locations on some edges that are transverse to this plaquette. And it turns out that this is still a commuting stabilizer Hamiltonian, and you can solve it exactly. Something like this model was written down by Levin-Wen a very, very long time ago when they were trying to generalize Levin-Wen models to 3D. Actually, I encountered it during my PhD. It's an example of a Walker-Wang model, if anyone's ever heard of one of those. Yes, Excellent. I'm not going to answer your question until the next slide to keep up the dramatic tension. All right. So you can still solve this model exactly. It's still going to be a loop gas. And the results of solving the model are going to look quite subtle and boring at first. So it's still a coherent superposition of these different closed loop configurations. But now what happens is that certain of the loop configurations end up getting these slightly mysterious relative signs. The rule for determining whether or not you get a sign or not has to do with whether the projection of this image along a particular plane has a self-twist in it. So that the fact that this has a minus over here has to do with the fact that this line has a kind of writhe or self-twist in it when viewed from this direction. So it's an anisotropic model. Likewise, it has to do with the fact that this has a writhe in it. Actually, the idiot-proof way of determining whether or not there's a sign is to take the loop configuration, shift it in the 1, 1, 1 direction, and then calculate the parity, the linking number parity of the loops in the two separate configurations, and this will give you the relative minus sign. Okay. All right, so that's the 3D fermionic toric code. Let's talk about its excitations. This will be the important part. So once again, we have vertex excitations and vortex lines, closed vortex loops. The closed vortex loops actually look the same as they did before. They have much the same character. They're actually created by the same operator, which is you act with sigma z along a surface. The vortex line forms along the boundary of the surface. The special new thing is that the vertex excitations are a bit different. The operator that creates these vertex excitations has to be a bit different because the plaquette terms are a bit different. So the sort of operator that commutes to the plaquette terms has to be a little different. So in order to create a pair of vertex excitations, yeah, you pick a line along the lattice, you flip all the spins along the lattice, but you have to decorate it with some z's transversal to the path. And those extra decorations ensure that this operator commutes with the Hamiltonian along its length, except at its endpoints where it creates some excitations. Okay. Those extra decorations are incredibly important because actually they endow these fermionic quasi-particles, or they endow the vertex excitations with a fermionic statistic. In other words, if you create some of these fermions by opening up this line operator and you exchange a pair of the fermions, you get a relative minus sign between those different configurations. And so this is special because we've started with a model that microscopically has bosonic degrees of freedom, and we have an emergent fermion. Okay. All right, that will be important. Okay, so what happens at finite temperature? So once again, at any finite temperature, the vertex defects proliferate immediately, entropically. It's just guaranteed. And once again, in fact, the phase diagram is exactly this, at least has transitions in exactly the same place as the bosonic toric code. So once again, the vertex excitations proliferate. Once again, there's a low but non-zero temperature regime where the loops are small. And then there's a regime where everything is proliferating, the vortices and the point-light particles. And the claim here is that there's actually still something special about this region. It'll turn out that this region has an emergent two-form symmetry, anomalous two-form symmetry, and that's going to be enough to show that it's non-trivial in the sense that we said before. Okay, so I'm going to give you a sort of outline of the proof of how this works. So, and we're focusing on this low but finite temperature regime. So basically, the point is going to be that there are vertex defects everywhere, and there are short loops. Okay. And the point is going to be that you can remove those short loops by doing just some local operations. Okay? And once you've removed the short loops, you again get this loop-like symmetry. So once you've removed the vortices, if you move one of these fermions in a circle, it turns out that the state returns to itself. Okay? Because it would only not return to itself if this line ended up linking some vortex excitations. Okay? So this cleaned up state has this emergent symmetry, and this symmetry has an anomaly in the sense that it creates fermions. And the conjunction of those two statements is enough to show that this state is not trivial in the sense that I wrote down on the second or third slide. Okay, so we'll do a little bit more of the details there. Oh yeah, I should tell you a little bit about how the loop cleaning works. So basically, the probability of having a loop of length L decays exponentially without. That was the Piles argument. So it turns out then that you can do a sort of naive estimate of this, and it's just true, is that the longest loop in the system will tend to be at most log L in length. So if you subdivide your system into boxes that are just a bit larger than log L, we chose log L squared, we could have chosen something a bit weaker than that, and you clean up all the loops that you can clean up in each one of these boxes, and you do a few rounds of this, just like 4 rounds of this, you can show that you can clean up all of the loops with a probability that approaches 1 in the thermodynamic limit. Okay? So basically, in the low temperature phase, you can remove all of the loops with high probability. And this is the sort of algorithm that we sort of came up with. So let me now just, and let me call that loop cleaning channel, I'll call it C for channel. Okay. So here is basically the logic. We start with our fermionic toric code state at low but non-zero temperature. We do our loop cleaning algorithm. It gets rid of all the vortices with essentially probability 1. I'll call the resulting state rho phi, or rho empty. Okay? Okay, what we're going to show is that rho empty is not trivial. And then the next stage of the proof, we show that rho empty, which has been obtained, if rho empty can be obtained from our initial state by a simple channel, then the initial state is also similarly far from any trivial product state. Okay, so it's a sort of 2-step thing. You clean up the loops, you show that the resulting state is non-trivial. The cleaning operation is not very disruptive and it's very local, and that ends up implying that the original state is also non-trivial. That's the way the argument works. Okay, so there are a few steps. Yes? No, the channel reads the configuration of the loops and locally corrects them. It's a bit like Glauber dynamics. Yeah, a bit like that, yeah. Okay, so, yes, okay, so I've said that there's sort of 2 parts. So at first, so here is where I use one of these results from Lili and Yoshida that I mentioned on a previous page. So first of all, I need to tell you that rho empty is non-trivial. That's one of the things that we need to show. The state where the loops have been removed is non-trivial. So this state where the loops have been removed has the higher form symmetry I was talking about. If you multiply it by the fermionic loop operator, you return back to the correct state. And if you open up the fermion loop operator, it has these emergent fermionic fermionic statistics. Those 2 statements taken together and using a lemma, or adapting rather, a lemma from Lili and Yoshida, ends up implying that rho phi is not trivial. So topologically ordered by the definition I gave before. Then we have to, so that's sorry, I'll put some inequalities on this page to satisfy people who are maybe already sort of following this. But basically, we adapt Lili and Yoshida to say that rho empty is far away from any trivial product state. And the way that we say that mathematically is that the fidelity between rho empty and any trivial state is exponentially small in system size. Okay? All right. Then we have to go back and show that the thermal fermionic toric code state is also non-trivial. And there we use a data processing inequality, which basically says that the fidelity between the fermionic toric code and any trivial state is bounded above by, roughly speaking, by the fidelity between rho empty and something else that we can show is trivial. Okay? Those 2 statements together tell us that the fidelity between the fermionic toric code state and the trivial state is bounded above by the fidelity between rho empty and a trivial state. And this is decaying faster than any power law in system size. All right, so that's basically how the argument works. Okay. Right, okay, so that's basically the end of the talk. So I can answer any questions you like about that. All right, yeah, good, yes.